This may be the first talk session I've ever attended where it started ahead of time. I'm very excited. There must be just enthusiasm brimming in this collective group. So I hope this won't disappoint. And I think you all know I've been following, had an interest in the three-body and n-body problem in various contexts in recent years. And today I wanted to talk mostly about the three-body parameter and about the going beyond the three-boson problem. And this work has been generously supported by these agencies. So I do want to stress that the work I'll talk about today involves in various ways most of these collaborators, Kevin Daly, who's here, and Nirav Mehta, and Jose, and I think you know everyone else. I could have put Dort on here, but she wouldn't fit. Sorry. But really, it's been very helpful to work with these talented people on these challenging problems. So I wanted to just start. So a lot of you know kind of the basic way we've been approaching these methods in recent years using the hyperspherical picture, but I thought for those of you who might not know, I would go through it briefly. So the idea is that we're solving a partial differential equation in 3n minus 3 dimensions. We aren't tackling the problem now with external fields present, so we can remove the center of mass. And so for instance, for the j equals 0 states, you just get a simple three-dimensional partial differential equation after eliminating the trivial Euler angle degrees of freedom. And we break the solution of this up into basically two major steps. The first, it's kind of a divide by conquer strategy, you might say, where we first diagonalize parametrically as a function of the hyperradius r. We diagonalize the Schrodinger equation in the theta phi part of Hilbert space. And this gives eigenvalues and eigenfunctions, a complete set of eigenfunctions in those hyperangles at each hyperradius, and it gives energy eigenvalues that are dependent on a coordinate that we can interpret as potential energy curves. And then, in principle, this can be expanded into a complete set of the eigenfunctions with coefficients that depend on the hyperradius. And this basically recasts the Schrodinger equation in any number of dimensions, this strategy, into coupled ordinary differential equations in the hyperradius for the radial functions with non-adiabatic coupling terms, these P and Q matrices that are calculated. I haven't written the formulas, but they're calculated in terms of the R dependence, R derivatives of the eigenfunctions. To do this first step, that's usually actually the hardest part of the problem, especially as you move into more and more particles beyond 3. But for 3 particles, you can just hammer this with basis spline variationally, and this can be done essentially exactly for any two-body interactions. You could write down this technology is quite well advanced, and it grew out of Brett Esri when he was in my group. And for more than 3 particles, the most efficient method we've found so far is the correlated Gaussian basis set, okay, where the Gaussians depend on the interparticle distances. And in some cases, when you're going to higher symmetry, there are additional vectors in the problem to give the j greater than 0 and parity states that you're interested in. With this method, we've only gone to, and with some recent extensions by Kevin Daly, we've gone up to 5 particles. But I think it looks promising that we can go and do a few more particles. Some people like the Kievsky group or Nir Barnia, they have made progress using hyperspherical harmonics. We also toyed with this in the 80s, but I've mostly abandoned this method except for exploratory studies. Just to give you a few ideas of kind of what happens when you do this diagonalization and you get the hyperspherical potential curves. This was the first study of Joe Masick that introduced this method for 2 electrons in a helium atom. And one nice thing that came out of this study was a very simple interpretation of the main experimental result back in the 60s when he did this work, which was that in photoabsorption studies of helium near the doubly excited states, there was one dominant channel out of 3 near the n=2 threshold that could have possibly been observed. There was one clearly strong signal, and you can it kind of leaps out at you on this graph why one channel might dominate. There's really one potential curve that goes to much smaller hyperradii and is really the dominant excitation channel in that system. This was the first clue that Ugo Fano really leapt on, and Qidong Lin, and started pursuing this as a more general avenue for solving the few body problems in general. Another important example that you can view as closely connected with Masick's method is Efimov's original study, which predicted basically a 1/r² attractive potential curve as a function of the hyperradius when you have infinite scattering length in a 3-body system with short-range interactions. And in fact, he's also calculating energy as a function of hyperradius, and basically you can view his paper as an application of this adiabatic picture, but it's in a limit where this is an exact treatment. But in a sense, Masick's treatment is a generalization that allows you to use this even in cases when it's not exactly separable, the hyperradial degrees of freedom. A couple of other examples that we studied, for instance, 3 helium potentials, 3 helium hyperspherical potentials, where you just have one dimer bound state, and all the rest of the channels represent 3-body continuum states. And so, for instance, one of the processes that we are very interested in the group is 3-body recombination, where you would come in at some incident energy in the very cold gas, come in on one of the 3-body channels, and you could make a non-adiabatic transition to the 2-body fragmentation channel, and the system could then break apart into a helium dimer and a helium atom. In nuclear physics, you can extend these ideas. Kevin Daly has been collaborating with me and Alejandro Kievsky to get the 3 nucleon potential curves, and similarly you get a potential curve going to the deuteron bound state, and then the rest of the potentials, only 2 shown here, would represent 3-body continuum states. So you could describe either a neutron collision with the deuteron breakup as coming in on the lowest channel and then going out on the continuum, or the time reverse would be 3-body recombination of 3 low energy nucleons coming together and making a non-adiabatic transition to form a stable deuteron. Another example pushing to the 5-body problem is a recent study Kevin Daly made, again with pushing correlated Gaussians to treat now 5 bodies, 2 positrons and 3 electrons, and these are some of the lowest lying potential energy curves. And we're in the process of trying to understand some of the scattering physics that goes on in these kind of processes, in these kind of systems. Okay, so Efimov is well known in this community, and of course he made this startling prediction long ago that has now been clearly verified by experiments, and we're looking into more and more finer details of the Efimov effect in universal physics, where the scattering length is the dominant length scale in the problem with the unitarity limit of these few body systems. And this was the first experimental confirmation of the Efimov effect by the group of Rudy Grimm from Innsbruck, a Nature paper in 2006. This was a prediction we had made in 1999 of the topology we expected as you sweep out the three-body recombination rate. Here it's plotted as a recombination length, which is the 1/4 root, proportional to the 1/4 root of the recombination rate, which is expected to be a straight line with some quantum modifications, and showing an FMOV resonance, the first of an infinite number, and a destructive interference minimum that we can give a nice simple interpretation to, although I won't get into that today.
Those are different scattering length, the experimental theory?
Yeah, this was a model system, whereas this is really the cesium atom. So at this time we just picked some model. I think actually there are different models plotted here which are different symbols. Some were Sech-squared potentials and some were rescaled Leonard-Jones potentials. So the energy spectrum, going back to FMOV physics, is known to look like this, as displayed nicely in this Brottenhammer review, where you get the infinite number of levels at unitarity, which would be 0 on this 1/A axis. And then the observables in low energy, in cold gas experiments, are where these trimer bound states become unbound, where they merge into the low energy, essentially 0 energy continuum of the three atoms, like would be relevant to collisions in a Bose-Einstein condensate. So these are the points where experiments are now seeing resonance effects in three-body recombination. And some of the predictions that we made and others subsequently made using effective field theory method, this infinite number of destructive interference minima, well, the infinite number hasn't been seen, but 2 separated by this FMOV scaling factor of 22.7 have been observed. And in this experiment in 2009, gave some of the first evidence for these multiple FMOV features separated by the FMOV scaling factor. And so the key predictions are, again, that FMOV resonances should occur at large negative scattering lengths, and there should in principle be an infinite number of them, although they're getting larger and larger by the FMOV scaling factor, so eventually you'll see only a finite number in any gas of a given finite density. At positive scattering lengths, on the other hand, you see these destructive interference minima. And this 8⁴ scaling is really there, which makes it a little difficult to imagine exploring the Bose gas at unitarity. Although there's a recent study by the Gilla group that I won't talk about today. I think Jose may discuss that a little bit in his talk toward the end of the week. Experiments where they've been looking at the many-body system, looking at the behavior of this system at unitarity. But there's a January Nature Physics article by the Cornell and Ginn group, if you're interested in getting a heads up about that. But I mean, the obvious conclusion is it would seem like this would be a really bad idea to try to make a Bose-Einstein condensate at unitarity because of these explosive losses. But one of the interesting results was that the Gilla group could see a system living of the order of a millisecond, which is plenty of time to learn quite a bit about the system, even at unitarity. This is a paper I like to show to illustrate the excitement of few-body physics, the kind of exponential growth of the number of citations of FMOV's paper. Okay, so one of the important issues is to try to understand where the first FMOV state should appear and what controls that. And for a long time we thought, and I think the whole theory community thought, that the first FMOV state should more or less appear randomly and be almost unpredictable without really doing a detailed calculation for whatever Hamiltonian you have at interest. experimentalists were always asking us this annoying question, where is that first Efimov state? And we always said, well, it's going to be anywhere. Who knows where it will be? Don't ask me. It can't be predicted. And so we summarized this viewpoint in this paper back in 2009, with Brett Esri and Jose, and documented how changing Hamiltonians could change around this, the appearance of the first Efimov resonance. So we thought everything was nicely understood, but then there's a paper, and this is a quote from our paper, that in general, knowing the two-body physics is not enough to tell you where the three-body Efimov resonances will occur. Because in general, we thought that a three-body parameter had to be separately specified in addition to the two-body Hamiltonian. But what I have started calling the bombshell PRL by the experimental group forced us to completely rethink this conclusion. And basically, at least for a class of potentials, a class of two-body interactions, this is now known that you can at least approximately predict where the first Efimov resonance should be. You can approximately predict the three-body parameter just knowing the two-body physics. So let's discuss that a bit. Of course, whenever the experimentalists provide us with strong evidence, we kind of take it on ourselves as theorists to try to get to the bottom of this. So we started right away after we heard this result trying to see if there was a way we could understand this within our framework. And it took about a year, but eventually our results were published in this physical review letter in 2012 that my PhD student Jia Wang worked with me and Jose and Brett to put together, and did a whole lot of calculations to really document this new universality and track down its microscopic origin. Other theory attempts or efforts, I might mention Cheng Chin had a toy model, which I didn't take too seriously, to be honest, and I think it doesn't capture a lot of the key physics here. But anyway, it was it was the first thing published, I think, after the 2011 experiment. There was another group who was tackling it in a somewhat similar spirit to what we were, not assuming universality was true necessarily, just doing lots of calculations to try to get to the bottom of it and see under what conditions would it be universal. And their paper, I think, never went beyond the archive preprint stage. I don't think it appeared in a journal, although they have a very recent physical review letter, which is kind of an outgrowth of this early study of theirs. There were a couple of other treatments that seemed to reach different conclusions than us. But maybe I won't talk about them too much. One by Schmidt, Rath, and Sverger, and another by the Fedorov-Jensen-Zinner collaboration.
So what is the difference?
Of these, or of what, or of all these?
No, not, you said these two last ones, which they're different.
Yeah, let me try to remember what was different. I think the Zinner study was also used, assumed a broad resonance model, but it seemed to conclude that as the number of two-body bound states went off to infinity, there would be no convergence at all of this parameter. Whereas our results showed rather strongly, and I think the new results of Ueda give even stronger evidence that for van der Waals potentials, it's very flat and independent of the number of...
What does mean universality in this case?
It means...
What's the meaning of it? Because universality means it doesn't depend on the system. So in this case, it seems like it's a particular system.
Yeah, in fact, we toyed around with calling this a quasi-universality because it's saying basically for every atomic system this should be so, because what we end up predicting is that the van der Waals potentials and probably other power law potentials have, you can, once you know the tail of the power law potential, you can predict where the first Efimov resonance is. You can predict the three-body parameter. That's what it means. But it doesn't extend all the way to...
Depend on the system, though. Is it true or not?
It does for, say, nuclear systems. I think basically we would say we could not. But for atoms, if I tell you the van der Waals length, or if you tell it to me, I can tell you where the first Efimov resonance is. I can tell you the three-body parameter. It's not random. To within about 15%.
How about atoms with unequal masses?
That I'm going to come to later. It's a more complicated story because there's such a bigger parameter space.
So what you're saying is that the three-body parameter in case of atoms depends only on two-body interaction. This is the statement. Is that correct?
To within approximately 15%.
Well, that's what's to be expected, you see, because in nuclear physics you have three-body forces, and it's not the case, obviously.
Well, atoms have three-body forces too.
Well, so why they don't influence it then?
Well, let's get into the qualitative origin. It's really something special about the van der Waals potential that kind of ends up shielding the system from those short range.
So very short range ranges don't.
It's kind of shielded.
So some kind of medium range would count.
Exactly. That's how it ends up
Doesn't
working.
make clear from what you said. Yeah. Okay.
Let's see, with the other paper that I didn't address, I think this might have been a two-channel model. Do you remember, Jose? The Sverger? So anyway, I'll show some comparison with experiments, which I think kind of rules out the treatment of this paper.
Richard will be here, I think, in a couple of weeks. And
Oh, okay.
maybe he will talk about it. And then we also have Artem here from the Jensen group, so he can maybe comment on that in the afternoon as well.
Yeah, I think they maybe have revised the theory of this publication a little bit so that maybe it doesn't disagree with experiment as violently as the first attempt. But anyway, it didn't really solve that, and I think there's evidence against this Fedorov-Jensen treatment. Okay, so to summarize some of the evidence that, again, it was really surprising to me and to most of us working on Efimov physics, that when people looked at many different Efimov resonances, the value of the scattering length, again, it's negative, so it's written as the absolute value of the scattering length divided by the van der Waals length at which the Efimov resonance was seen. You can see they're always around 10. The scattering length is always around minus 10 times the van der Waals length. This was the big surprise for us.
How big is the three-body state in comparison with van der Waals length?
It's around 10 times, I guess, the van der Waals length.
Okay. That might explain why you have 10% changes.
Well, it is correlated with that statement, yeah. Is that right? Yeah, I think that's around 10 times would be the mean value.
Resonance, it's the size of the...
It's the size of the barrier, which is maybe 1 to 2 times the scattering length. Okay, so what we did was try to see, our first premise was that what was maybe at work here was that the two-body Hamiltonian, I mean, one difference from nuclear physics is for atoms, the potentials are very deep and they have many, many two-body bound states. And so we sort of thought, well, maybe the models we had done to date, sometimes Sech squared, which were short range, sometimes Leonard-Jones and so on, didn't seem to show this universality. Maybe it was because of that we didn't have enough two-body bound states and it might kind of saturate. So we started doing more and more complex models with many, many two-body bound states. You can see all of these are going to two-body fragmentation thresholds, and the Efimov physics is occurring in a tiny energy range near threshold that you can't really even see on this scale. But with Jia Wang, he was able to improve the technology of solving for the three-body recombination rates, and now we can do problems of this complexity.
Now, on the plot that you have r, little r, is that the same thing as the...
This is the van der Waals length, yeah.
So it was L on the previous slide.
Yeah,
right?
yeah, I guess I'm not too consistent in my notation. And so basically what we were able to do is for different potentials, like for a such squared potential, increasing the number of two-body bound states in the S wave only, that gives the scattering length where the first Efimov resonance occurs in units of the van der Waals length. And you see it did show some signs of saturating for even short-range potential, but at least early on, like for a nucleon-nucleon system where you don't have many bound states in the, you have a big deviation from these are the experimental values, by the way, all the ones I showed on the previous graph. But for two different variants of the potentials with van der Waals tail, one, a soft wall potential, I forget if it was the green or the blue, and one with an ordinary Leonard-Jones two-body interaction. We found these values always line within this band of around 15% around this value minus 10 van der Waals lengths. So
Could your statement maybe translate in the fact that effective range corrections are important in order to study the first Efimov state?
we found it didn't correlate so well with the effective range.
Because Efimov had the correction to the potential coming from the effective range, and I'm wondering if these two things are not correlated with each other.
I mean, Jose, you
He
probably...
wrote about 10, maybe a little bit more than 10 years ago, I think, a sequence of papers where he corrected the 1 over r squared, the way terms coming from effective range. And basically what you're saying here is that the effective range, because van der Waals length is correlated to the...
I think it's a little deeper, though, than just the effective range
so
alone.
it's more than that, so you have the next order correction. Yeah?
Well, I'm not even sure that you can write it as an expansion in effective range. But anyway, we're not really trying to do that analytically. We're kind of studying the numerical evidence for this and dive into the numerical origins. But we did try to correlate these results with effective range, wouldn't you say, Jose? And we found the correlation with van der Waals length much clearer. Although when we do such squared, we did sort of do a conversion because there is no van der Waals length for a such squared potential, and we use the effective range to map the two-body results into this scale.
Maybe just to add one thing to this. The funny thing for Leonard-Jones potential is that it doesn't matter how many bound states you have, the effective range is always the same. When there's a universal relation between the scattering and the effective range. So for Leonard-Jones potential, all these guys there, all these energies does have the same, exactly the same effective range.
Which means they have the same Leonard-Jones length.
Yeah.
But then it means there is a correlation.
So
So is that this statement, your two statements don't seem to agree then?
Right, but these would all be exactly the same. I mean, assuming our numerics are solid, if that were true. But there is some variation.
Has anybody studied the limit of infinite number of S-wave bound states?
I haven't seen that, except, well, maybe the Zinner paper, but I don't remember which potential that was for, if they were doing van der Waals or such squared. But they were trying to see an extrapolation to infinite number and claiming it had no limit. That was the claim of their paper. So once we started seeing these stable numerical results, then we wanted to interpret really if we could we understand qualitatively what might be going on to prevent the system. Apparently, if you see all this complexity at short range, coming in the Efimov channel, there are all these avoided crossings. You would think there would be some sensitivity to all this rich short-range physics that would be very non-universal. Which has always been our expectation because we knew that this kind of forest of frightening complexity was lurking. But then what we found was for instance, if we just look at the Efimov channel, that one channel that has this 1 over r squared attraction at large distances, we found that it has a systematic deviation from the Efimov potential, which is here, this 1 over r squared potential predicted by Efimov physics. We found it's more attractive, but it's almost independent of the number of bound states. There are many potentials here shown, and these are the Efimov channel potentials from 1 to 10 bound states, two-body bound states. And you see the thing that fascinated us is that there is this strong barrier occurring at about twice the van der Waals length. It's almost in an identical place for all these channels, and you can easily imagine that if you have a three-body collision and it's going to be blocked at about 2 van der Waals lengths from penetrating any closer to any smaller hyperradii. And that is basically what is shielding you from all that non-universal short-range physics. Now, next we tried to see what is special about the van der Waals potential, and Jose and Ja especially did lots of graphing of the wave functions and so on to see what was different. And so they started looking on the hyperangular wave functions to see what is really going on. And so, for instance, when you have the van der Waals force field, there is like a suppression. These rays are like the two-body valleys where two particles are trying to come close together. And you can see there's a big suppression of the three-body wave functions in those valleys, the two-body valleys of the three-body Hamiltonian. And on the other hand, for a such squared potential, there is far less suppression. There is the wave function extends much more robustly into the two-body valleys. So it really seems there is something very different qualitatively about the van der Waals potential that is preventing or suppressing the wave function in these regions. Now, it had been hypothesized that possibly quantum reflection, as two particles come together, right, as two particles come together in a van der Waals potential at near zero energy, say particles 1 and 2, right, then it's known, like from the work of Grabachen and Flambaum, that semi-classical approximations break down at around the van der Waals length. And in fact, in some studies like Friedrich, he would claim at low energy you have a quantum reflection. Basically, as two particles come together, they tend to reflect off of this point. And so that was an early premise that we had in mind might be causing this shielding from the short-range physics. But you know, you can look quantitatively at this problem, and you can see that, in fact, the de Broglie wavelength is not much longer than this cliff that you have to plunge over. And so, in fact, we were able to, through these quantitative studies of the de Broglie wavelengths, pretty much rule out this quantum reflection as an explanation. On the other hand, we know, like from WKB, right, you have a wave function that has an amplitude which gets small when the wave function has a very deep, very high kinetic energy. And then you have the usual phase stuff, right? And basically, you can think of this amplitude in front as just a classical suppression of the wave function. It's just 1 over the velocity, which says that as you go between r and r plus dr, the time to spend in that region is small, going like dr over the velocity, local velocity at that point. So in the end, that's, I guess, the main crux of our interpretation is that in these valleys, it gets so deep, so fast, that the particle has a very high kinetic energy in this two-body degree of freedom. And a high kinetic energy in the hyperangles, that translates into a large hyperradial effective barrier. Okay, because it's kinetic energy in the hyperangles that is this lambda squared over 2 mu r squared, part of the Hamiltonian. So this is getting big whenever two bodies are probing this region. That's kind of our qualitative way of interpreting this result. And so one thing we were able to do was actually give an analytic form of a potential curve that should sort of be part of Efimov physics in any system with a van der Waals tail. I guess I didn't give the formula here, but it's in our PRL for the effective potential, which deviates quite a bit from the Efimov potential. Throughout this region, it's more attractive, and then here it has this strong repulsion that the Efimov potential, of course, does not have. But it's always this barrier at around twice the van der Waals length. Now, one of the things I should say is that all those model calculations we showed were for a two-body Hamiltonian model that would correspond to what you would say is broad Fano-Feshbach resonances. That is, they are just assuming a simple potential between the two particles. It's not got the two or more channels that you would need to, if you wanted to describe narrow Fano-Feshbach resonances. And so it was more or less believed, we thought this, I think, that these results we were finding and presenting in this physical review letter were only applicable probably to the broad resonances. And for very narrow Fano-Feshbach resonances, Efimov physics near those might be more likely to show non-universal three-body parameters. But then this experiment came along and again provided a surprise. For a single atom, 39 isotope of potassium, they were able to observe 7 Efimov resonances. Now these were not 7 going to a single Fano-Feshbach resonance. This was the first resonance for 7 different Fano-Feshbach resonances. And they went over a whole range of two-body resonance widths from 0.1, which is deep into what we would call the narrow limit, up to 2.8, which is broad Fano-Feshbach resonance. And they published this in last year in a PRL. So this was a bit of a surprise to us. Here is their data. You can kind of see this is 3 potassium atoms, and almost all the resonances are fairly close together. These are all fairly broad resonances with this two-body resonance width parameter from 2.8 to 1. But they also had 2 narrow ones, which were showing Efimov features in just about the same place. And again, this was a surprise. And in some ways, it might be expected if this van der Waals shielding of the short range is really what's important. Well, all of these channels, narrow or broad, they do have that. But we're still trying to explore this systematics, and Yujun Wang and Jia Wang have both done a lot of calculations with two-body models now. But we haven't really, I wouldn't say, made a simple story out of that so far. They seem to see more sensitivity to the short-range physics with their two-body models than this experiment is suggesting.
What are the blue curves there?
The blue curves, I think, are fitting. I believe the experimentalists like to fit the Brottenhammer formula for three-body to their curves to try to extract the position of the resonance.
Are the two-body models now multi-channel two-body interactions?
Not for these curves. I think these are fitting the usual one channel. But what I just mentioned, Jia Wang and Yujun, they are doing calculations now with two-channel models. So this is a comparison of one of the two-channel models, the one of Schmidt, Rath, and Sverger. And you can see it would seem to predict as the resonance width gets smaller, that's toward this end of the scale, a much stronger variation from this unitary or universal limit of the three-body parameter, which is not really seen, at least in the potassium experiment. But it'd be interesting when Schmidt is here later if I think they have an improved version of this, which maybe doesn't fail so badly.
So those experiments include both narrow and broad resonances?
Yeah, these are the two narrow ones, and these are the broader ones.
For broad resonances?
Yeah.
Correct.
Yeah.
Okay.
So there is a very recent PRL, I think, just a week ago or so, by the UETA group, Pascal Nadon and Shimpe Endo in his group. And they've done a very detailed study using separable interaction models. They have a way to map these van der Waals two-body interactions onto a separable Hamiltonian, a separable potential, and which they feel captures the van der Waals physics adequately. And they've also done other potentials like an 8-4 potential, which is kind of like the 612 Leonard-Jones, except with r to the 6th replaced by r to the 4th. And they more or less confirmed what we found when they did many different van der Waals potentials as they varied the number of S-wave two-body bound states. I guess they went up to 10 also, which is about where we stopped. And you can see for van der Waals potentials, you get a very stable three-body parameter as you change the number of two-body bound states. For a 1/4 potential, they're also seeing, once you have, I guess, maybe you don't stabilize till you get two bound states, but you get very stable results also, but a different convergence. And for some 1/r to the n, as well, they also get some these results. So they are basically seeing reasonable agreement with our conclusions, I would say, and I think this is some quantitative support for our calculations. I think their separable model probably leads to more stable and more accurate numerics than ours. Although it may have the limitations of the separable approximation. But they do have some comments which are a little hard for me to interpret, that they seem to be saying that they disagree with us in some of our conclusions, even though their numerics pretty much verified what we had claimed. One thing they say that I have difficulty understanding, I don't know if you've noticed this comment, Jose, is that they say at large separation, the system has an elongated geometry due to its Efimov nature, but it must deform to an equilateral configuration to accommodate for the mutual exclusion between the particles. Now, by mutual exclusion, I think they're talking about this classical suppression effect here. Again, the fact that the amplitude of the wave functions in the two-body valleys is very small. But from our studies, I don't really think elongated describes at all the Efimov states we've looked at. The wave functions in the hyperangles are pretty much constant. I mean, they're not an equilateral triangle especially, or not linear especially. It's probing all geometries. And at least when I see the word.
They mean to the fact they have the hyperangle. In the hyperangle, you see that there's certain angles which are favorable.
No, but it's not really so. At least our.
This is what I'm saying.
That's yeah. I mean, to me, elongated would mean maybe kind of almost linear-ish triangles, but we don't find those particularly favorable at all in the plots we've made. We don't. I mean, this configuration and this, they're all about equally probable.
So when you superimpose different potential energy surfaces, you have different lambdas, which is this hyper thing. So how different are they?
I'm not sure I know what you mean by superposing different
Well,
surfaces.
you have this lambda over r squared, lambda, whatever, lambda plus lambda. You see the hyperspherical area.
Right, so if you had no interactions, you'd have all of these. And
They depend on the hyper quantum number.
Sure.
If it's called lambda, right?
Sure.
Lambda squared, I don't know exactly what's the power there. So there might be different lambdas there, which lead to different angular dependence on the.
Well,
right?
no, but I mean, this is the Efimov channel. I mean, they aren't looking at these repulsive three-body channels.
So those don't play any role.
Well,
So
that,
you can exclude them. You see, that's my question about. You see, if you can exclude them or not. You see, if you don't exclude them, then they might.
I mean,
that you have-
this operator doesn't commute with a Hamiltonian, and so
Yes.
if you want to use this as a basis set, you'll find you need many, many of these. So I'm not real sure what you mean. I mean, there aren't single lambdas in these potential curves, especially in the Efimov channel. It's very slowly convergent when you expand it in this lambda hyperspherical harmonic expansion. It's very slowly converging.
But to me, that would mean that non-equilateral configuration will also be important. So that might mean that.
Yeah, I'm not saying it's unimportant, but they're claiming it's the dominant configuration. Yeah, I mean, we said this is just exactly as important as this. And they seem to say that the Efimov state is more, almost all that,
Okay.
which we don't agree with. Okay, anyway, so their words seem to imply they disagree with us, but I think their numerical results largely agree. And one nice thing about this paper that I'd like to understand better is they claim to give a quantitative way of predicting the three-body parameter once you know the two-body potential and the zero energy wave function in that two-body potential. And so they may have a nice analytical tool that'll help to shed some light on this problem.
Are you using the same numerical method?
Well, I think they are also doing adiabatic hyperspherical, and in that sense, I think they're mostly doing what we are, except that they're using the separable potential, which does, I think, simplify their numerics a bit. Okay, so now for some of the newer news. Well, I guess this goes back to February, so it's not newer, except this is only in preprint stage, which is, despite all these observations of Efimov physics that I've been talking about, really no one had a demonstrable evidence for multiple Efimov states. And remember, we're predicting an infinite number of these in keeping with the Efimov effect. There should be an infinite number of scattering lengths that have, for each Fano-Feshbach two-body resonance, that have three-body recombination resonances. And this is the first paper I'm aware of that really has strong evidence for a second Efimov resonance. Well, there might have been some evidence which was not as strong for the three fermion system in lithium-6. But anyway, I think this is certainly by far the clearest evidence. This is the second Efimov state at a larger scattering length. And sorry, it's cut off a little at the bottom, but they're plotting it in units of this Efimov scaling factor 22.7 times the scattering length A minus where the first Efimov resonance was seen, divided by the actual scattering length. So at 1, if Efimov scaling were exact, you'd expect this resonance to be right at 1 on this scale. And you can see it's close to that, but shifted a little bit. And in the end, their analysis of their data is that this would translate into an Efimov scaling factor of 21.1, which is approximately within the error bar of the Efimov scaling factor, but not exactly nailing it.
You mentioned fermions, lithium-6. How would they do that?
They have 3 different magnetic substates.
Yeah, but then the parameter is much. No, they probably it's the scattering.
It's kind of amazing coincidence that there's a region where all 3 scattering lengths of these 3 spin states, they're all large. And I forget, are they large and negative? They're like 700-800 or something like that.
I see, okay.
So it's kind of an interesting accident that all these three different scattering lengths were all large and negative there. That was work by Selim Yakim, and also, well, I think the one that saw two resonances was O'Hara, wasn't it?
But they can have at most one resonance probably, right? For that.
What do you mean at most
If
one?
Emo state, if Emo state.
Probably, yeah.
Probably at most and be close to the threshold.
Yeah, I think if you would have to get very close to one of the individual resonances, and there, two of the scattering lengths would get large, but not all three. But the one that they observed, they were all three pretty large. So anyway, this is kind of not unexpected, but a nice reassurance that all this is really probing FMOB physics. I always wondered the first time I saw the Rudy Grimm's data in 2006, okay, if you see one resonance, how strong is that evidence for the FMOB effect? Because, well, we know these systems have resonances all over the place, and maybe it could accidentally be some other type of resonance. But once you start seeing this FMOB scaling factor, then that pretty much is the nail in the coffin.
Chris, am I misunderstanding? The Zakanti et al. Paper you're distinguishing that because it was the minimum?
Yeah, exactly. Yeah, they saw two minima. Yeah,
Okay.
that's right. But this is the first time a second resonance, I think, has been really definitely seen. And for a long time, people have been interested in heteronuclear systems. In particular, the system of two heavy and one light is predicted to have a much more favorable FMOB scaling factor, even though only two of the three scattering lengths in the problem are resonant, going to the heteronuclear Fano-Feshbach resonance. The scaling factor is predicted to be 4.88 instead of 22.7. So it's much more favorable to see multiple FMOB features. And this very new preprint by Cheng Chin's group at Chicago, in fact, is claiming to see three features attached to a single two-body resonance. And I guess, well, these are the three. Okay, that's the lowest
Both
one,
sides of the
the
resonance
second.
or-
No, they're all on the negative side. And they do, I think the first one is around minus 337, and then they see another one here at, 1,500 or so, and then another one 4.8 or so times higher. One thing that concerns me a little about this is that they shifted what was thought to be known about the two-body resonance position. They shifted that by about a Gauss. So really, for this to be true, and for the FMOB scaling factors they measure to be what they claim, there would have to be a pretty significant revision of the scale of the two-body interactions. And there's no separate data yet that is evidence that that's correct. I think one has to either measure the binding energy as a function of magnetic field on the positive side, or something else to get evidence that this revision of the two-body physics is believable and credible. Because if this resonance were where it was thought to be before this measurement, the FMOB scaling factors would not look very much at all like this 4.88. I guess I have a little time to talk a little about the heteronuclear theory. We had made some predictions actually about the heteronuclear case in this project spearheaded by Yujun Wang with Jia and Jose as well. And we did find some universality for this system, but it's a much more complicated universality. And you can, I think, easily see why it's going to be much more complicated, because now the parameter space is suddenly much larger. There's a mass ratio between the two heavy atoms and the light atom, and there are two different van der Waals length scale in the problem, and there is a background scattering length for the two equal atoms. So in the end, we just mapped out the three-body parameter as a function of many of these variables and made predictions for several of the atom systems that we knew were of interest. So first of all, it's only really Efimov favored and plausible to do an experiment if the two like atoms are heavy. You want them to be heavy. If the two like atoms are light, it's almost going to be impossible to see an Efimov effect. But this is an example of what that parameter space looks like if we map out essentially the three-body parameter in the form of the binding energy at unitarity for the unequal particles as a function of the inverse scattering length for the two like atoms. And you can see there is a trend. The numerical results are pretty much following a simple curve, and these would be the first three Efimov resonances. But it does vary if you have a very small like atom scattering length or a very large one. But of more interest for experimentalists probably is this table of predictions of where the Efimov resonance and where the interference minima should appear. And for instance, for the case that has been studied experimentally, our prediction was that you would see an Efimov state around minus 1,400. Now, there was some ambiguity in these calculations as to whether this was the first or the second such Efimov resonance. And in fact, based on Cheng-Chin's new experiment, it seems clear this would be the second. And so if we divide by the scaling factor, this 4.88, it actually gives, I guess I wrote it down here, slightly below minus 300 compared to the experimental resonance position of 337, negative 337. So it kind of got in the ballpark, but it's not such astonishingly wonderful agreement. But at least there is some evidence that maybe these predictions in this heteronuclear paper have some validity, at least approximately. The other thing maybe worth mentioning is that this cesium-lithium resonance is a fairly narrow one. I think the S-res parameter is less than 1. So it's starting to be not perfectly fitting the broad resonance scenario. And that could be also causing some non-universality. We're really not sure. So I was going to just say a few things about clustering physics, what happens as you study the N-boson problem with large negative scattering lengths. As you know, if you have a large negative scattering length, there will be no high-lying two-body dimer. But as you make the scattering length more attractive, right, the scattering length gets more and more large and negative as you're going from left to right on this scale. There are some interesting regions, like there should be a point where you have just enough attraction to bind 8 bosons together, but nothing smaller. You can't yet bind 7, 6, or anything smaller. And then if you go a little more attractive, there's a point where suddenly now you can just bind 7 bosons, but nothing smaller. And these fall into a universal pattern, it seems. This has actually 2 calculations, one from Dorte Bloom, who was studying helium clusters when she was in my group. These magenta points. Helium is very close to unitarity in its natural scattering length. And Javier von Stecker, who was looking exactly at unitarity with some short-range models like Gaussian potentials. And interestingly, the binding of these clusters pretty much follows the number of triangles you can make out of the atoms in the cluster, showing that that's this Greene curve, which kind of shows that the binding is is controlled mostly by a three-body interaction here, which is kind of the Efimov binding. Each triad is bound by Efimov physics. And at least for the lowest few clusters up to 6 or 7, it follows this trend fairly well. So anyway, this was Javier's prediction, for instance, of the universal points in inverse scattering length where you should see a 4-body recombination resonance and 5-body, 6-body, and so on. Once you know the 3-body, which now we think is actually universally determined by the van der Waals length, you should be able to predict the scattering length of all these other points. And so since I'm out of time, I'll just maybe flash up experimental result showing that in fact the experiment has confirmed where the 4-body, there are actually 2 4-body resonances, and these are comparison with our 4-body recombination calculations. And from Rudy Grimm's group, their experiment. And this dashed line is where this universal prediction places it. And for 5 bodies even, there is evidence that a 5-body recombination resonance is right where it's expected as well. So this is the largest such universal cluster of this type that's been observed. But it appears that there is strong evidence for this universality. And not only that these are determined by once you know the 3-body parameter, but now we also think the 3-body parameter, at least for van der Waals potentials, is universal. Yeah.
When you go from 3 to 4, 5, you add in the recombination rate of power, the scattering rates to power 3. So for example, 4-body recombination rate will be proportional to 8 to 7.
Yeah, dimensionally
So
you expect that.
It will be 8 to the 10.
Exactly, exactly. So maybe I'll stop there and just kind of obvious points pointing in concluding in the direction of the issues I've talked about. So thanks for listening.
Questions?
You see, I just looked to see, I haven't had it yet, I looked to see this paper by, it was 91 actually by Few-Boson. He computed the correction coming from effective range and found the potential proportion to 1 over r cubed in the hyperradius. I'm wondering, because you find it more attractive, you probably can extract from there the power and see if that corresponds to the same.
It looks like the effective range over the hyperradius cubed, you're saying?
Correct, yeah.
But even at finite scattering length, there's a correction of a over r cubed.
That's what he says, you see, but you find this at very small hyperradii, around 1. And that sounds reasonable, you see where you find some. But anyway, you can extract the power law there, the correction, and find out if it's...
Yeah, that would be interesting. I
believe, you see, his arguments are pretty general, and probably they would be applicable to what you are doing.
I see. Yeah, I would like to check that out.
Yeah, it's PhysRef 1991.
Okay, thanks.
PhysRef C.
Oh, PhysRef C, okay.
So you have to look into that.
Maybe just to comment on that, we've used Efimov's formula.
I'm sorry?
We have used that treatment of Efimov, and
Mhm.
at least for the energies, if you have a finite range interaction, it really improves the agreement with the numerics.
So it does work.
At the energy level, it does work.
Mhm.
As the wave functions, we had more trouble, but that might be a problem on our end. But for the energies, it works actually beautifully.
I think he computed only the energies in that paper.
Yeah.
So not anything else, and he used a perturbation theory, and therefore the wave functions you have to work a little bit harder to generate.
I know Jensen and Fedorov, they had a paper, right, where they put in the effective range into a zero-range model, and that actually does turn off the unphysical collapse at the origin, but I think it didn't work very well, is my recollection, in terms of anything quantitative. Do you recall, Jose? I thought we looked at that once.
These corrections, effective range corrections, they're always correcting the long range behavior, right? But so you might be able to
What do you mean low range? Small hyperradius?
The hyperradius is much larger than the range of interaction. That's where these extensions work.
Yeah.
So that
But
that
that's
by
about, you
itself-
see, what you have here in this plots, you see, if I
Well,
look at them.
what really determines the value of the energy is going to be the median hyperradius, when the hyperradius is about the range of interaction.
Look, if I look at the plots of the hypersurfaces you have, the main correction is in the region of 1, R over the van der Waals.
Yeah,
line.
twice is
So
where the
you
barrier
go-
is.
Go a little bit further back, you see, because you have the plots. You see, over there, yeah, no, the previous one, I think, you see that. Yeah, over there, you see the inset. So you see, everything happens, you see, it's relatively small hyperradius.
Yeah.
And that's where 1 over R cube will dominate, not at large.
Sure.
Well,
that's consistent
so it
with
seems
what
like
it was.
what you're saying is Efimov's result might explain
Yes,
this,
that's what I
this
said.
deeper attraction,
Yes, that's what I
but
said.
probably not the barrier.
Oh, no, but that will be already short-range interaction, and that's the parameter which you do, you see, but I'm talking about this.
Yeah,
Because the wave function becomes small there anyway if the potential is very deep.
yeah, that's certainly very possible.
The repulsion there becomes irrelevant.
Was
at one point.
I'm sorry, was Efimov's correction attractive?
I'm not sure now. You see, I tried to figure that out, but obviously the effective range changes sign depending on the. You see, it's not fixed, but you see, Dorothy says that she looked at that and she agrees with that formula. So
Yeah, but we use, I mean, I should add to this, we didn't use the van der Waals interaction, we used the simple Gaussian potential.
Yeah, no, but-
Gaussian
yes.
potential, but
Okay.
it worked quite beautifully, actually.
So it will be interesting to see if that's 1 over R cubed. That's a pretty simple interpretation.
Hmm. Yeah.
So I have a question on the next slide, since you're here. What is the, it seems there's a big difference between the van der Waals, which have the parallel tails, but the hyperbolic secant potential kind of looks similar. What am I, even though it has kinetic-
Yeah, well, we found when you get this many bound states, if we kind of reinterpret the effective range as a van der Waals length, then it can be put on the same scale.
Okay, so you have to tune the effective range.
Yeah,
Match this.
that's-
If you don't, then you don't get, okay.
That's right, yeah. I mean, of course, there is no van der Waals length for the such squared, but it did seem like with many bound states, this was starting to show some universality too, if you made that. Yeah.
I'd like to repeat Sheena's problem a little bit more. So can you comment on the universality of three-body parameter when they have different masses? When have different masses?
Well, that was just what I showed at the end, that there's this big parameter space, right? It depends on all these things. It's different if the two like atoms have 0 scattering length, or if it's near infinite, or somewhere in between. It depends on that. It depends on the mass ratio. It depends on the two different van der Waals lengths. All these, in principle, are going to come into that. So we think our evidence is that it looks universal once you specify all these other parameters, but it's a more complicated universality. It's not just giving a number like 10 times the van der Waals length.
I have a question about this theoretical calculation in which you assume that the total potential for the three-body system is the sum of the three pairwise potentials.
Right.
How well is this approximation justified? If the distances between the atoms are of the order of the van der Waals length, I mean, what's the correction to this simple sum of the three pairwise?
Well, at those distances, it's quite small. I mean, that would be the range of distances where it's Axelrod-Teller physics, and I think it's starting to be important at around 1 van der Waals length, and so at 2, I think it's probably already fairly small, but we didn't quantitatively test that, although we put in the Axelrod-Teller in that earlier JPhysB article. Although even there, I think we had to increase its scale by a factor, didn't you, to see any effect at all?
If you use the typical parameters for an alkali species, this three-body force doesn't make any difference in that, because is it 1 over R to the 9?
Well, it depends on geometry. In some geometries, it is more like 1 over R6, I guess. But at least in the equilateral, I think it is 1 over R to the 9.
Yeah. So, yeah, to see difference, you have to use very unphysical parameters for that interaction.
Any other questions? Not sure. Let's thank you, Chris, again.
Thanks.
Just a reminder, if you're interested, please join us for the lunch at the